Hello and welcome to InsideWi-Fi, Video 8. Free Space RF Propagation Loss. Have you ever wondered why your Wi-Fi signal drops the farther you walk away from your router? Even in a completely empty room with zero obstructions, radio signals naturally weaken as they travel. Discover exactly how this happens, how engineers calculated and why 5 GHz networks behave differently than 2.4 GHz networks. Free Space RF Propagation. When an antenna emits a RF wave, it releases electromagnetic energy. In an ideal environment with zero obstructions known as free space, this wave behaves like an expanding balloon. To understand this principle, imagine the antenna as a point source radiating RF energy uniformly in all directions. As the wave moves away from the antenna, it forms an ever-expanding sphere. The total transmitted energy remains the same, but it is distributed over an increasingly larger area. Consequently, the energy density decreases with distance, resulting in a weaker received signal. Formula for free space RF propagation loss. For line-of-sight communication, the free space path loss, FSPL, in decibel can be approximated using the formula. Path loss L equals 32.4 plus 20 times the base 10 logarithm of F, plus 10 times N times the base 10 logarithm of D. Where F is the frequency of transmission in megahertz. D is the distance in kilometers and N is the path loss exponent whose value is 2 for free space communication, indicating how fast the signal attenuates with distance. The higher the transmission frequency, the higher the propagation loss is for the same distance. For non-line of sight communication, the free space propagation loss is the combination of the equation plus many other factors such as attenuation due to absorption, reflections and multipath. Path loss equals 32.4 plus 20 times the base 10 logarithm of F, plus 10 times N times the base 10 logarithm of D plus attenuation. In a mixed environment, such as an indoor office environment, a different path loss exponent value may be used instead to approximate the path loss. For example, a value of 2.5 to 4 may be typical of most indoor environments, though the path loss exponent can be as high as 8 in some RF unfriendly environments. For example, the free space loss for 2.4 GHz at 100 meters from the transmitter is about 80 decibels. If the radiated power is 30 decibels or 1000 milliwatts or 1 watt, the received signal at 100 meters will be minus 50 decibels, which is equal to 0.00001 milliwatts. Therefore, in 100 meters, the RF signal loses 99.99999% of the power. Path loss comparison between 2.4 GHz and 5 GHz. 5 GHz signal attenuates at a greater rate than 2.4 GHz. As higher the transmission frequency, the higher the propagation loss is for the same distance. For example, the RSSI at 1 meter for 2.4 GHz is minus 40 dBm, and for 5 GHz is minus 46 dBm. The RSSI at 34 meters for 2.4 GHz is minus 70 dBm, and for 5 GHz is minus 77 dBm. The RSSI at 67 meters for 2.4 GHz is minus 76 dBm, and for 5 GHz is minus 83 dBm. The RSSI at 100 meters for 2.4 GHz is minus 80 dBm, and for 5 GHz is minus 88 dBm. Higher the propagation loss is for the same distance. From the last example, 2.4 GHz provides better coverage over longer distances. 5 GHz offers higher bandwidth but experiences greater propagation loss. As distance increases, the difference between 2.4 GHz and 5 GHz signal strength becomes more noticeable. Key takeaways: RF signals weaken naturally as they spread through space. Signal attenuation occurs even in perfect free space conditions. Higher frequencies experience greater propagation loss than lower frequencies. Real-world environments introduce additional losses through absorption, reflection, diffraction, scattering and multipath. Understanding path loss is essential for designing reliable wireless networks and optimizing access point placement. This is why a Wi-Fi signal that appears strong near an access point can become significantly weaker just a short distance away, even when no obvious obstacles are present. Let me know your thoughts in the comments if you found this video informative and helpful. In the next video, let's see effective inverse square law on RF propagation. Thank you for watching.